Hello and welcome to NASA Science Live. I'm Stephanie Smith from the NASA headquarters social media team, and we are coming to you live from sunny Central California, Vandenberg Space Force Base to be precise, where hours from now, DART, that's the Double Asteroid Redirection Test, will be lifting off. There's tons of activity going on inside the NASA hangar, so come with me, we're going to take you inside. You're going to meet scientists, you're going to meet engineers, and by the way, we're taking your questions. Just go ahead and use the hashtag AskNASA. Or if the feed you're watching has a comment box, pop your questions in there. Moderators are standing by while we take you behind the scenes. Heck, we've even got the shipping container that DART came in from the Applied Physics Lab. And this is the hangar where the launch commentary will be tonight as we get ready to blast off for a date with an asteroid. You might be wondering, does that asteroid pose a threat to us now or after the test? And the short answer is no, it doesn't. In fact, there are no known asteroid threats to Earth for the next 100 years. But it doesn't mean that we're not keeping our eyes on the skies. We'll get into all of that and more on NASA Science Live, but first, let's do a deep dive on DART.
In case there was an asteroid coming towards Earth and you're there, you can actually stop it. I mean, that's kind of fantastic.
NASA is crashing a spacecraft into an asteroid.
What? You think science fiction, but this is real.
Never in my life would I have thought I would take a couple $100 million spacecraft and crash it into an asteroid. My name is Michelle Chen.
I'm Lena Adams.
My name is Kelly Fast.
I'm Andy Rifkin.
I'm Justina Surovets, and I help tell the story of the DART mission.
I'm a planetary defender.
And I study how the orbits of asteroids change after we hit them with spacecraft.
My job was primarily to make sure all the systems on the spacecraft work together.
The DART mission is NASA's first test of a planetary defense technique called kinetic impactor.
DART is the Double Asteroid Redirection Test.
It's just a spacecraft that is going to go and smack an asteroid.
The moonlet Dimorphos, which orbits the asteroid Didymos,
And see if we can change its trajectory just a little bit.
in order to show that we can deflect incoming asteroids if we need to.
DART will only be changing the period of the orbit of Dimorphos by a tiny amount.
But in space, just a little bit is just enough to make an asteroid actually miss us.
In the event that an asteroid is discovered well ahead of time before it might impact Earth.
Behind me, you see the spacecraft.
It's really cool to see it coming together in real life.
It is fantastic to see it in real life.
To see it turn from ideas into real pieces that are going to go into space.
The solar arrays will actually roll out to 28 feet in length.
Once the solar arrays are deployed, it's going to be the size of a school bus. As the solar array opens out, it's going to swing out in this direction. The asteroid's only 2 football fields in size.
We're flying at over 6 kilometers a second.
30 days out, we see 1 pixel on our field of view.
You can see Didymos and Dimorphos as one point of light.
About 4 hours out, our spacecraft becomes autonomous.
And then that's where everything gets really exciting.
You actually are seeing impact.
We're super excited and nervous as well.
I feel really honored and humbled to be working in an area of science that has such a broader impact, figuratively and literally.
No DART! The dinosaurs are made completely extinct by an asteroid impact so many years ago. Here we are, we can actually do something about it. I think this is just wonderful.
Well, now that you've had a chance to see what DART aims to do, we know you've got questions. Let's go ahead and meet the folks who've got answers. Joining me now are Dr. Lori Glaze, the Director of Planetary Science at NASA headquarters, Lisa Wu, Mechanical Engineer at Johns Hopkins University Applied Physics Laboratory, or APL for short, and then also from APL, Dr. Nancy Chabot, the DART Coordination Lead. All right, well, thanks so much for being here. How are you feeling on launch day?
Amazing, exhilarated. I mean, I just can't even believe this day's here.
So excited, so excited. Got to go out and look at the rocket this morning, and it's on the pad, and we are so ready to go.
It is just so amazing. We are on the pad. We're gonna launch tonight.
And it's beautiful here in
so
California.
nice.
Yeah, Vandenberg Air Force Base, Space Force Base, man, old habits die hard, can have some really, really thick marine layer and clouds, but the skies are clear, and let's hope for a good liftoff, but also clear skies and good visibility.
Exactly.
Okay, so this show is all about questions. I'm going to start with a few of mine, and then we'll get to yours. Okay, so Lori, the big question, why is the DART mission important? Why do we have to do this?
Great question. This is a really, really important mission because it is humanity's first ever mission to try and deflect an asteroid to help us prepare for a potential danger in the future. So what we're going to try and do is move this asteroid, just change its orbit a little bit, and demonstrate that we can actually do this. This is really, really important that we do this now when we are in a point where we don't know of any asteroids that are potentially dangerous right now, that are a significant threat, I should say, those that are a significant threat over the next 100 years. But we want to test this technique so that if and when we discover an asteroid that might be a potential threat, we have this tool in our belt and we're ready to go.
Luck favors the prepared, so we want to test the technology before we need it.
Absolutely.
Okay, all right. Now, Lisa, on the engineering side of things, you have been with this mission since it was a little baby CAD drawing, and now it's a full-fledged spacecraft sitting on top of its Falcon 9 rocket. Oh man, can you tell us more about this amazing machine, how it works, what are its parts, how is it going to do the job it's made to do?
Sure, of course. So part of the DART spacecraft, we have this instrument called Draco, and it's basically a camera, the eye of the spacecraft, if you will. On board, we also have this algorithm called SmartNav, built at APL, and together, these two things work as the eye and the brain, and that is how we will go and get to our target. And then on the spacecraft, of course, because our #1 mission is to impact this asteroid, that means, we can do a few more technology demonstrations. So we have some really cool technologies like the ROSAs, the Rollout solar arrays. Those are really cool because they literally roll out like a yoga mat, and those are solar arrays. We have our NEXI ion engine, and that's going to test out the ion engine. We also have our high GaN antenna that uses a radial line slot array. So there's so many cool technologies on this mission, and I'm just so excited to have been part of it.
You're like a glowing, proud parent over there. Are you
Basically.
Sure? Are you sure you're going to be okay when you destroy your spacecraft by slamming it into an asteroid?
I worked really hard on spacecraft, but this is for the science. So I'm okay with it smashing this asteroid.
Okay, for the greater good?
Yes, for the greater good.
But one follow-up question on that. If you destroy the spacecraft, which is what you intend to do on a successful day, how will you know? How will you see it?
So when we're approaching this asteroid, Draco will be sending all these images back to Earth until it doesn't. And then 10 days before we actually impact, we will be deploying a CubeSat, and that CubeSat will be taking pictures of the entire impact. So we will also be getting all of that really cool pictures. So stay tuned.
All right. Okay, from engineering over to science. Nancy, this is the first time that we're doing a test of a kinetic impactor. What are you most looking forward to about this test?
Well, I'm most looking forward to how much we actually deflect this asteroid, right? I mean, this is a test, and these asteroids aren't a threat to the Earth like we were talking about, but we want to do this test before we need to be ready. And we're not really sure exactly how much we're going to deflect it. We know it's a double asteroid system because telescopes. There it is.
Yeah, we've got a handy dandy
how
model
handy
here.
Is that?
Yeah,
we know it's
a Didymos, right?
Didymos is the main one.
And not Didymoon, but Dimorphos.
Dimorphos is the smaller one, and it goes around like clockwork every 11 hours and 55 minutes.
So we're coming around.
Sure.
Just like a
going
clock.
Around every 11 hours and 55 minutes. And telescopes on the Earth discovered that this was a double asteroid system and know this, and that's why they've gotten this down really precisely. And so what's going to happen, it's going around.
Okay, we're coming around.
And then the DART spacecraft's going to come and slam into it head on. Oh, thank you, Laurie. That's perfect. And there we go. DART spacecraft totally destroyed. How are we going to know how much we deflected it? DART spacecraft is not going to tell us. The Italian Licia CubeSat is long gone after some spectacular images. Telescopes on the ground, again, are key to this mission. And we think we're going to change it by maybe about 10 minutes. So the clock will be more like 11 hours and 45 minutes going forward, but we're not really sure. Could be less, could be more, and that's what I'm most excited about learning. And because this is bigger than DART. DART is just the start. We're doing this first test, but we want to understand this to potentially protect the Earth in the future. So I think that also makes this really exciting, that it's not just this one test, but how are we going to apply it going forward?
Fantastic. Okay, so those are some of my questions. What are your questions? Remember, you can use the hashtag AskNASA if you are on Twitter or Instagram. If you've got a live chat like on YouTube or Facebook, just pop your questions right there and the moderators will get those over to me. And as they do that and we begin to ponder your questions, here's one more for you to ponder. How will DART deflect an asteroid in space? We asked astronauts Shane Kimbrough and Thomas Pesquet to demonstrate in microgravity.
Hi everyone, I'm Thomas Pesquet and I'm with my favorite astronaut Shane Kimbrough up here on the space station. Today we're going to talk about a very cool new NASA mission. It's called DART. Can you tell us and tell me a little bit more about what is NASA's DART mission and what does NASA DART mission stand for?
Okay, yeah, so DART is NASA's first planetary defense test. So we're gonna try to do something we've never done before with the spacecraft. DART stands for Double Asteroid Redirection Test. So a nice acronym. NASA does like acronyms. DART is another one. Now the purpose of this spacecraft and this mission, it has one purpose, and that's to crash itself into an asteroid and try to redirect it or try to move it into a different orbit.
So today, Shane, we're gonna demonstrate some of those principles that you laid out before, but can you tell us exactly how we're gonna do that?
Well, I can try. It's the first time for us, but we're gonna try to demonstrate this asteroid kinetic deflection method, which is really the moment that spacecraft crashes into the asteroid. So we're gonna use microgravity up here because we have that all the time. And we're going to try to show you kind of how this is going to work when the asteroid is hit by this spacecraft called DART. So here we go.
So what I'll do, Shane is going to be the asteroid, and I'm going to be the NASA DART mission. On this CTB, more exactly, it's going to be a spacecraft. I'm going to try to throw it, and we'll look at the effect of that mass coming at him and the kinetic energy transfer from the CTB to Shane. Shane will be perfectly stable. It's not an easy task. You ready? All right, here it comes. I've redirected Shane successfully. Pretty good. A while ago, we got out the door and we got some new solar arrays here on the space station.
And so the same technology we have here now on the space station is going to be used to power the DART mission on its way to this asteroid.
ROSA, in case you didn't know, but you knew, it stands for ISS Rollout Solar Arrays.
So we got a chance to go outside and install the very first two of these new IROSAs, or Rollout Solar Arrays, on the very end of the space station, out on the port side. These are different because, for one, they're much lighter and smaller. To me, they look very fragile when we were picking them up and moving them, but they're rolled up. So when they launch, they're kind of rolled up into a compact cylinder, which is great for launch conditions. And then once they get up on the space station or in space for a satellite or something, they can then roll these things out to be useful. And so the same technology we have here now on the space station is going to be used to power the DART mission on its way to crashing into an asteroid.
And that's the kind of successful deflection that we're looking for. Okay, we're back with Lori, Lisa, and Nancy to answer your questions. Remember, hashtag AskNASA, or just pop them right in the stream wherever you are watching. Okay, first question, and this one has lots of likes. Joseph Forbes on Facebook asks, what of the law of unintended consequences? Is it outside the realm of possibility that a nudge might change an orbit from an innocuous one to one that does put it on a collision course with Earth?
Yeah, and that's a really, really important question. And it's important to understand that we chose this system here, Didymos and Dimorphos, specifically because it really provides the perfect test case for this experiment. where we have no chance of that unintended consequence. And the way I like to think about this is the little moon here, Dimorphos, if you could imagine a high school football stadium that's full of rocks, that's about the size of that little moon. So you imagine that big football stadium that's full of rocks, and then you take a refrigerator and you ram that refrigerator into that big pile of rocks. So it's going to make a little bit of a little tiny change in the speed of that little moon, but not very much, just a tiny bit. But over time, it's going to go around Didymos, and we're hoping to slow it down. Nancy can talk about that a little more, how we slow it down and it goes around. But overall, this whole system, Didymos is like a half a mile across. It's big compared to Dimorphos. So when we make this little change to Dimorphos, the overall momentum of this system is pretty much going to be the same. It will not even be detectable what we've done. So it really is exactly why we chose this kind of a binary asteroid system for this kind of experiment. That's one of the reasons why it provides such a good example that we really, it is no risk.
Physically impossible.
Physically impossible.
We're not going to set off a billiard ball reaction in space. Okay, so everybody rest easy. Okay, moving right along. Okay, well, maybe not Keith. Keith Taylor asks, I've heard some scientists say that if an Earth killer asteroid was headed our way, you'd need 5 years to spot it, get to it, bombard it, giving deflected shards enough time to deviate their path and miss us. Is that true?
Yeah, warning time is really what you want. And this is really why it's important to understand that planetary defense is much more than just deflecting asteroids. You need to be finding all of the asteroids. This is key to planetary defense, knowing where the asteroids are, characterizing them, tracking them, assessing, collaborating internationally, because it's a global concern. We're all on this planet together. And then mitigating, doing something about it if you need it to. And that's where DART comes into this one larger strategy. And so really you want to give yourself this warning time, because something like this is just a small nudge which adds up to a big position change over time. So the asteroid and the Earth theoretically wouldn't be on a path to hit in the future on a collision course. And this is why you need this warning time, and you have to do so much more to find the asteroids. And there's actually a lot that we need to do on that still. I guess maybe you want to pick it up there, Lori.
Yeah, I do. I want to add just a little bit to that, because what Nancy said is so correct, that it's critically important that we identify the asteroids and then characterize them so we know their orbits. And so right now we have ground-based telescopes that are observing the night sky every night, looking and searching for these asteroids. We actually also have a space-based telescope called NEO-WISE, which was a repurposed astrophysics mission that was originally called WISE, and it's out there also looking for asteroids. But we know there's still many of these smaller asteroids out there that we haven't discovered yet. So we actually have a new mission that we've just started called NEO-Surveyor, the Near Earth Object Surveyor Mission. And it's just getting underway now, and that's going to be a really powerful mission when it gets launched a few years from now, that its sole purpose is to really every day and every night to be searching the skies, looking for these asteroids, essentially the same size as Dimorphos, helping us better understand what the potential threats are that are out there.
Always keeping those eyes on the skies, right? Okay, so back to little Dimorphos here for a second. What's going to happen to the debris from the asteroid?
Well, the debris is actually, we think, going to be an important part of the experiment. So we think DART's going to come, well, DART will come speeding in at 15,000 miles per hour, and it's going to crash into Dimorphos, right? But we think that ejecta is going to go off in the other direction and actually give it even an extra push, like a little jet engine that shoots out from it, right? The rocks shoot out from it in the other way. And but how much of that happens is one of the reasons that we want to do this test on a real asteroid too, because real asteroids have different shapes and different sizes and boulders, and how are they put together and what is the strength. So then these debris though is very, very small. It'll stay with the system, and again, no threat to the Earth whatsoever.
All right. So let's go over back to engineering. Yadi on Twitter wants to know, how do you know if it worked?
Well, you see, we have this camera, Draco, as I mentioned before, and that's going to be sending pictures back to Earth. And about 4 hours out, that is when SmartNav, the brain of DART, actually will start taking over. So we will not be joysticking the spacecraft from Earth. It's fully autonomous 4 hours out. And then at 1 hour is when we actually will start seeing the smaller asteroid. And SmartNav will start firing off thrusters, getting it closer and closer to its target until, we will hit it.
Okay. So, question for the entire panel here. Logan on YouTube wants to know, how long have you been working on DART?
Oh, I think Lisa should start on this one.
Okay, because I think we've got, you're coming at this from a lot of different angles.
Correct.
From sort of the NASA science and business side,
right.
Engineering, building, and then the science that really starts with, with that impact.
Yeah, so I've been on DART for 5 years about when I started and joined the DART team. So NASA started initial development phase of DART in 2015, and I started shortly after that on the project as well. And it's just been a joy to join this team. One of the things that I love about being on a team like this is it takes so much different expertise to all come together in order to accomplish something that's so much bigger than any one person could do on their own. And DART obviously is a key example of that, and I'm just overjoyed to be a part of this mission.
Yeah, so I've been on DART for 3 years. This is my very first spacecraft, so I'm super excited for launch and the fact I was a part of building the spacecraft. Like, how many people get to say that? I built the spacecraft, like, wow. I'm just a few years out of college, so, like, to everyone out there, this is so cool.
No, you got your foot in the door at APL.
Yes.
And you did a rotation there?
Yeah.
That landed you
Yes.
on DART?
So right out of undergrad, I went to APL, and I was in a rotation program where I went to all different types of groups at the lab. One of my projects was DART, and I really liked it, so here I am 3 years later.
That is so cool. That's
And
so cool.
Did you green light this thing? Or do we have you to thank for this mission, Lori?
Well, I've been paying for this mission, yes.
Thank you.
Thank you very much.
But so I joined NASA headquarters about 3.5 years ago. And prior to that, I was a scientist and doing my research at NASA's Goddard Space Flight Center. And of course, I knew about DART, but I was not specifically involved with DART. But when I came to headquarters in my current role, DART is a part of my overall portfolio for planetary science. And when I look across our entire portfolio, I was so excited to actually have DART be a part of this when I came in, because we have a lot of great science missions, but we only have one planetary defense mission, or we did at the time, now we have two. But at that time there was only one, and DART. I thought, we have an amazing opportunity with this mission to tell the world about how important it is that we defend our planet and get more planetary defenders out there. And so it's been a really, really important part of what we do in planetary science.
Okay, so, all right. From the personal stories back to the science, Nancy, Jake Smith, 9287 wants to know, could asteroids be the reason water came to Earth?
Oh, that's a great question. Yeah, I mean, asteroids are fascinating objects. They're the relics of the early solar system. They were the building blocks of the planets. And so they really did bring a lot of important stuff to the planets. Water might have been one of them, along with other materials. That's really an active area of science that's fascinating. And we have some other missions that NASA's doing that are really in a position to address that, specifically like the Osiris-Rex mission. So maybe, Lori, you want to say a few words there?
I'll say a few words. We're here to talk about DART today, but I will give a quick shout out to the Osiris-Rex mission, which collected a sample a year ago in October and is now on its way back to Earth to bring that back. And that's a particularly special asteroid because we do think not only did it have water-bearing minerals on it, but also organic molecules. So not just delivering water to Earth and other planets, but also the building blocks for life. And as Nancy says, these are fantastic relics of the early solar system that each tell us different parts of the story of how our solar system formed and evolved.
I think that's what's neat about asteroids, too, is that you kind of can look in the past, right? You know, these things that are before the Earth, right, that we can look back to see how they did. But we're really talking here about the present, right? You know, with what the current threat to the Earth might be from these, and then preparing for the future, where we can be ready to do something about this if we needed to. So it sort of spans this whole thing with asteroids.
Yeah, well, Osiris-Rex is on the minds of others too. Astro Balrog on Twitter wants to know, does the DART mission have a volunteer ambassador team like Osiris-Rex did? And if so, he wants in, or she, or they. But Astro Balrog wants in.
Okay.
Planetary Defenders, would that
Planetary Defenders, I think that's the best way to go there. And you maybe have the URL there for the, Planetary Defenders.
Stay tuned. You have to wait a little later in the show, but we'll tell you how to be a planetary defender.
And I will say on the DART website, we recently posted some great outreach materials, so you can go under outreach on the DART website, and there's a kit where you can build the DART spacecraft out of blocks.
That's so cool.
Yeah, I saw that the other night. It's awesome. There's a virtual spacecraft that you can kind of go like Pokemon Go and like put it out there and take your, see it in your scene, and some other fun things. So definitely there's a lot of stuff ramping up, and check that out.
Okay, so back to our system. Seth on YouTube asks, how close are Didymos and Dimorphos to each other? If you were standing on one, would you be able to see the other?
Yeah.
That model's to scale.
Okay.
And so this is the right scale for how it should be.
So I don't know if people are familiar with the Washington, D.C. area, but this is the analog that I have in my mind.
Okay.
The whole system, Didymos and Dimorphos, would fit between the U.S. Capitol building and the Washington Monument. So you can absolutely see the Washington Monument from the Capitol building.
Right.
And you would see Dimorphos from Didymos.
There we go. Okay, so Nancy, Lily Hall on Twitter wants to know, how long ago did you identify the target asteroid?
Well, there was the 1990s that this was discovered to be a binary asteroid system. A double asteroid system was the first time that that was seen. I mean, so, but, DART mission didn't exist then. So, it was sort of talked about in some science conferences and planetary defense conferences, this whole idea of a double asteroid system. Actually, one of my colleagues, Andy Chang at APL, was one of the ones who originated it. He likes to tell this story where he was exercising in his basement, and it just sort of came to him. And anyways, then he sort of shared it with colleagues who have been thinking about planetary defense, and Didymos is just the ideal target because of this double asteroid nature.
Nancy, do you want to talk for just a minute about how we know it's a binary asteroid and how we know what the orbit is of Dimorphos around Didymos?
Yeah, what's really interesting, right? I mean, and even if you look at the model, like those two are pretty close to each other. And from Earth, it just looks like a single point of light. You can't see that there's two asteroids there.
Especially if it's back
but, okay,
here.
so yeah, so when it's behind like that, right, what you only see the big one, so it's less bright. But when it comes out to the side, there it's brighter because you're getting the light from both of those objects in the same frame, and then it's darker, and then it goes around. And so you just map out the brightness versus time, take lots of measurements, and over this 11 hours and 55 minutes, this brightness versus time changes. And that's really a great way, and that's the same technique that's going to be used to figure out how much we deflected the asteroid. So it's a great story.
Okay, we're getting lots and lots of questions about asteroids, what we know, what we don't. So we asked a NASA scientist, does NASA know about all the asteroids?
Does NASA know about all the asteroids? Well, no. But the good news is we know where most of the really big ones are. They get closest to the Earth. We found more than 90% of these. That's the great news. But there are a lot more smaller pieces that are still out there that we haven't found. It's really challenging to find asteroids and comets simply because even though some of them are as big as mountains, space is incredibly huge, and these things can be really far away. In fact, we want to find them when they're very far away from the Earth, so we have lots of time to take action if we ever find one that's really headed in our direction. Asteroids are both a source of fascination, but sometimes fear, because we wonder, can they hit the Earth? It's really incredibly unlikely that a significant asteroid impact is going to occur in our lifetimes. However, that said, if even one happens, it could be really bad. And that's why we want to go out and look for these objects and make sure that the Earth and an asteroid never get too close for comfort. So does NASA know about all the asteroids? Well, no, but we know what we have to do, and we're on the job, and we're really glad to be part of Team Planetary Defense.
So as you can see, NASA has an entire team of planetary defenders working to keep our planet safe, and we want you. That's right, you can become a planetary defender today by visiting bit.ly.com/planetary defender and test your knowledge. If you do well enough on the quiz, you will be able to get a special badge that you can share on social media, #planetary defender, so that we can see it over on the social media team here at NASA. And with that, we're going to go back to questions. Okay, next one up is from Matthew Cummins. How do you determine what weight the spacecraft should be and its speed in relation to the weight and speed of the asteroid in order to change the asteroid's trajectory? All right, physics question coming at you, engineer.
Momentum, physics. So, as we all know, the asteroid is quite large and DART is quite small. We're about the size of a smart car and we weigh roughly like 1,360 pounds. So, you know, compared to how big the asteroid is, which, as you said, it's like a football stadium filled with rocks, we're like really, really small. But we are going super, super fast. We're going 15,000 miles per hour, which for scale is like 4 miles per second. So try going that fast. That's a really fast. And with that and, you know, momentum, you hit something, transfer momentum. That's how we're doing it.
The good old F equals ma.
Yes.
All right, my favorite equation.
Yeah.
Okay. Do you have favorite equations, or is that just me? Okay, just me.
I guess it's just you.
Okay.
We
Don't
love
leave
all
me
equations.
hanging, Internet. If you have a favorite equation, please post it in the chat, and I will go back and I will like it later. Okay. Calicini, Craig McGuire, how long is it going to take DART to get to this asteroid? Nancy, how long do you have to wait to start your science?
Well, once we launch tonight, and then it'll be 10 months. So late September of 2022 is going to be the smashing event, if you will. And so, yeah, thank you very much. I know there's a lot of bad puns out there, so I just embrace them. But yeah, then we'll use the telescopes on the Earth. We'll actually continue observing until around March of 2023, even, because we're timing this in 2022 such that the distance between Didymos and Earth is still large, totally safe, but is minimized. And so the telescopes on Earth are going to get the most precise data that they possibly can. They'll be able to observe for months in order to really get a measure of how much we deflected this asteroid. So,
and at this point in the day, it's still fall 2022, late September, early October. But how soon are you going to know when you have your date with Destiny?
At 10:22. When we launch at 10:21, as soon as we launch, then that'll set the date for DART's collision with Dimorphos. So
awesome, and then we can send out a save the date so that you can all join us back. Yeah, what do you say? Do you want to do another? We'll do another live show, right?
We should do another live show.
For sure.
Yeah, you'll be there, Lori, right?
Absolutely.
Okay. Slicefire on YouTube. What are your future plans? I'm going to give this one to you, Lori. What are your future plans for the use of this new technology that DART's going to give us?
Great question. So the first step, of course, as Nancy has said, is that we need to assess the data. We really need to learn from this experiment. We need to learn and understand, number one, how well the SmartNav system works, how well we're able to target the asteroid and impact it. And then we need to understand how well that momentum transfer actually happens. You know, we don't know necessarily if the rock is solid rock or whether it's just a collection of rubble, and that's going to make a difference on how effective we can transfer the momentum. So we need to really assess that data and understand how well did this technique work. We also have some other techniques that we've been studying and thinking about for asteroid deflection that we may want to think about perhaps for a future test or for comparison with how the kinetic impactor.
Other than kinetic impactors?
Yeah, so there's a couple other ideas that are out there that have also been explored and have been investigated. One is something called a gravity tractor. which to me sounds like science fiction, but it is actually for real, right? That you can, by adjusting the mass of an object, by maybe taking off some mass or putting some mass onto it, you can change its gravity field. And so it's possible to actually change that a little bit. Another thought that's been out there is to potentially take a nuclear device and detonate it, not detonate the asteroid. I'll make that clear. You want to detonate it near the asteroid to give it a bit of a push, a bit of a big force. And just for the record, we don't want to blow up an asteroid.
Nor do we want to hire a ragtag group of drillers to go out there and place it.
I think I saw that one.
What? Yeah, I just want to explain, though, why you don't want to, explode an asteroid, because a lot of people say, well, I've seen it in the movies, don't you want to just explode the asteroid? And the problem with that idea is that if the asteroid is on a collision course with Earth and you blow it up, you then not just have one rock coming towards Earth, you now have thousands of rocks coming towards Earth.
Now we have new problems.
And then we have new problems.
Okay.
So we really don't want to blow it up.
Okay.
So those are things that we're thinking about for the future. I already mentioned the Surveyor Mission, which is another thing we have in our pocket for the future. A really important part, as I said, to make sure we find all of the asteroids and then we know which ones are potential threat. Right now we know all of the asteroids. We think we know almost all the ones that are really big, the ones that could like wipe out the dinosaurs, that kind of size, but the smaller ones like Dimorphos and larger, we still know there's a lot out there we haven't discovered.
And obviously we're
really excited about the Hera mission too. So so the
Thank
European
you.
Space Agency is going to rendezvous with the Didymos Dimorphos system with the Hera mission in 2026, which is going to be great. They'll be able to see the crater made by DART. They'll be able to get the mass of Dimorphos and really characterize the system even more. So along with all of everything that Lori said, we have to figure out from DART. And we're still really working collaboratively with these two teams, as is important for planetary defense, international issue.
Absolutely.
Okay, so obviously Earth, we're all very, very invested in watching out for asteroids on a collision course with Earth. Origami Masters on Twitter wants to know, how often are there asteroid impacts with other planets in our solar system?
Regularly, all the time. In fact, we've even seen some of them from Earth. We've actually saw an asteroid, for example, that went into Jupiter's atmosphere several years back. That was kind of cool. On Mars, where we've been having spacecraft that orbit at Mars for decades now, we can see new craters all the time that are being created by asteroids that impact on Mars. So we know this is a process that's happening all over the solar system. At Earth, objects are entering Earth's atmosphere all the time, very small ones. We actually get reasonable sized meteorites that fall all the way to the surface and don't burn up on a regular basis. So they're pretty common out there, but hopefully the ones that are the bigger ones are not quite as common.
Okay, so we have teacher and her students all the way from Hawaii. Hawaiian Disney Mama on YouTube asks, aloha, my students want to know if the asteroid didn't hit Earth back in the day and wipe out all the dinosaurs, would dinosaurs still be alive today? We're going to test the breadth of your science.
That is
speculation.
That is a really hypothetical question, because there's so many variables at play there. So many different things that have happened since that time. It was quite a long time ago, of course.
Fair.
But the one thing we like to say is that the dinosaurs didn't have the Planetary Defense Coordination Office. They didn't have a planetary defender to help them save the day. So
they didn't
that's
have
what we're here
Lisa to
for.
build a spacecraft to go out there
That's right.
and save them all. Okay, but thank you, and we hope that you'll be watching.
Yes.
Okay. On to Shannon Wayne Bowman on Facebook. Ooh, will we get to see it crash live? And would we be able to see it with the naked eye by looking up?
So the images are going to come streaming back from Draco once every second, and we will be sure to get those images back before the DART collision happens. So they'll be sent and on their way, streaming back every 1 per second, and that's going to be information that we'll have here on the Earth. The Lichia Cube images will get transmitted back a few weeks later, and it'll take them a little bit longer, so they'll capture them and store them on board and then send them back after the fact. You're not really going to be able to look up and see anything with the naked eye. Again, this is like a tiny little nudge. We're changing it it, so you're not even be able to see it on that scale model over there. So it's not going to be the sort of thing that you can look up and see, but the images coming back will be spectacular.
And correct me if I'm wrong, Nancy, but I believe what the time of the impact, and Lisa, that the Didymos and Dimorphos will be about 6.5 million miles away from Earth. So it's a long way away.
Very far.
It's long, but it's not as long as a lot of things. It's actually pretty close in the things, but very safe. You won't be able to see it. You need some powerful telescopes to even be able to see how the brightness changes with time.
Okay, so this is not something that the home astronomer is going to be able to point their telescope at and find in the night sky.
No, no, that's not the plan.
Okay. We've got plenty of other stuff. We'll tell you. Just stay tuned. Okay. Now, for those of you who are just joining us, again, get your questions in, use the hashtag AskNASA. You can also pop stuff right in the stream, in the chat, wherever you are watching. And because some folks are just tuning in, we are getting a lot of some of the questions that you've handled. One that I think we have got like a public responsibility to touch on again is Donna, we hear you. Donna K. Bradshaw on Facebook wants to know, what if this puts the asteroid in a chaotic rotation that causes a horrible chain reaction and it becomes a threat to Earth? Lori?
Sure. Yeah, and again, I'm happy to answer this question as many times as you ask it because it's really an important question. And we chose this particular double asteroid system, this binary asteroid system, precisely because it does not pose a threat. There is zero risk of that kind of unintended consequence. The impact that we are going to have on the small moon, on Dimorphos, is very, very tiny. Thank you. Yes, will impact here, but that little impact is really not going to change at all. It has no chance of changing the overall system, of how fast the overall system's going or its path. So nothing will change in the whole Didymos system. It's going to stay exactly on the same trajectory where it is now, which is of no threat to Earth. It's not coming anywhere near Earth anytime in at least 100 years and probably longer than that. So
okay, so rest easy.
Yeah.
And enjoy the show too, right? Yeah. This is exciting. Chris Betancourt on Facebook wants to know, what kind of systems do we have in place to monitor potentially dangerous asteroids? We've talked about the ones that we know. How are we keeping our eyes on the skies?
Yeah, that's a great question. And we have many ground-based telescopes that are searching the night skies every single night, looking for potentially hazardous asteroids and comets. And we also have a space-based telescope, which I think I mentioned earlier, called NEO-WISE, which is an old astrophysics telescope that we took over for planetary defense purposes. It also is out looking for asteroids, but also characterizing them. And then we have this new mission, the NEO Surveyor, Near Earth Object Surveyor Mission, which we hope to launch perhaps in the next 5 years or so. That will be dedicated to searching for those new asteroids.
And you do work in conjunction with the amateur astronomy community, right?
Good point. Yes, we work with the amateur astronomy community, and it's a global network, right? Planetary defense is not something that's unique to United States or any particular country. This is a global issue, and there are many space agencies and others around the world that all work together to coordinate the observations. Someone detects an asteroid and they send a signal out to everybody that says, hey, I found this asteroid, and everybody points their telescope and says, let me follow up so we can better constrain just where that asteroid, what its orbit is and where it is and what it looks like, and characterize it, its size. So it is really an international collaboration.
And as a follow-up to that, Mark New on Facebook wants to know, what are the benefits of global creativity and global cooperation in such an important mission?
Well, I think the global cooperation is absolutely critical. If there ever were actually a real threat, we are all going to have to come together as a global community to help put all our resources together, whether it is to make sure we better define the threat, to put together whatever the mitigation plans are, to help protect ourselves from a potential threat. So this is an absolutely critical international cooperation.
And Lennon on YouTube wants to know, is there any other country openly working on planetary defense, or is it just NASA?
No,
right
I think Nancy just mentioned a couple minutes ago the Hera mission that's being built by the European Space Agency.
I mean, we've got Licia Cube, right?
Yes,
so
Licia
Italian
Cube.
Space Agency
It's already
actively contributed
We're
with there.
already-
And then, yeah, Hera from the European Space Agency. And so it really is people around the world and agencies around the world working together cooperatively for this. I mean, the database that you're referring to is all publicly available, right? I mean, you put it all into the same database. It's constantly monitored, updated, real time, and you can go check it out at the NASA website.
Yeah.
So to get a sense of scope, how many people have been involved in this mission? Maybe we can kind of tote it up from the different parts of NASA, even just represented by the three of you.
I'll pass it over to you guys. Let's see.
Yeah.
What's the size of your team there?
My engineering team, so mechanical engineering, we have about, I want to say like a handful, 10. But like there's so many people. We have our INT folks, our electrical folks. We have people who make our blankets, former seamstresses. We have our truck drivers who have to drive this spacecraft across the country. Like there's a lot of people. And I also want to note that like I've been working with like roughly 50% women, and that is so rare in an engineering field. So I'm so thankful to be working on a project where I have so many role models. It's super cool.
Great. And
yeah,
how about
definitely
the
the
science
team. If you have to do it, you should guess in the thousands, right?
Yeah.
I mean, hundreds is too low. Once you get to that the other day, I mean, like creating the DART logo, right? What you were talking about, so cool. I mean, it's just takes people. We have an APL, right? And then there's NASA. We have scientists across the country. We have scientists actually around the world on this team, and we have a lot of different partners. And really, thousands is going to be the right order of magnitude to get there.
Okay. So earlier, Lisa, you talked a little bit about some of the technologies that are on DART. Tween us on the internet. Natosha on YouTube wants to know, does DART carry any explosive devices?
No. I did not put any explosive devices on the spacecraft.
And Lisa would know.
I would
You were
know.
one of the last people to see the spacecraft,
Yes, I
right?
was one of the last people to see the spacecraft before we encapsulated. I know this thing inside out, so no explosives.
Fantastic. Okay, on to Facebook. Marcel on Facebook asks, why crash the spacecraft and not try a soft landing and then use the engine of the spacecraft to push the asteroid?
Goes back to momentum transfer, doesn't it? Yeah. Do you want to?
We are hitting this asteroid really, really fast. The amount of thrust we'll need if we, per se, landed on the asteroid and tried to, push ourselves, it's way, a lot. It's much easier just to use the momentum, or we already have 15,000 miles per hour to hit the asteroid.
Yeah, but I think Lori's point is good too, right?
Yeah.
I mean, that this is just one technology,
Exactly.
right? It's the most mature, it's the one that's ready to test now. Maybe in the future we'll want to have other tools in our toolkit. And people have talked
It is a
about
good
using
idea.
engines, specifically the ion engines, but you'd have to have it burn for a really long time, right? I mean, as compared to this instantaneous event, you would have to operate the spacecraft. And that's challenging in its own right, right? To have that sort of fidelity. And asteroids are not round. They have all sorts of complications with them, and landing is its own complication. So, but DART really is just the start. It's just the first test of one technique that you might use, and it'll be interesting to see what else we might develop in the future.
And you got to walk before you run, right? It is
Exactly.
a technical challenge in and of itself just to make contact with this. Okay. So, Lori, and that is another sort of tween us questions. Boo on Facebook, who's watching from Canada's East Coast, wants to know, if an asteroid was headed straight for Earth, would you inform the public?
Absolutely.
Also,
I don't even have to think about that one. We have, before you get to the rest of the question, we actually have not just a group that is collaborating and cooperating amongst multiple federal agencies in the United States, but working with other agencies around the world. We meet regularly. There are conferences every year to bring all of these various entities together and talk about what are we going to do and how are we going to communicate this if we ever had a potential threat. So absolutely, the public would be told. We would provide the best information that we have available, and we would start developing what the mitigation plans are, and also any kind of protection plans that we need for people. So there's no doubt.
And also, we couldn't hide it.
No.
No,
you can't.
Like you look up those amateur astronomers that we depend on so much to help give us more observations. Yeah. Everyone would see it.
As Nancy said, when we look at these data and we calculate the trajectories and their orbits, this is in a public database. Anybody has access to that. So
as soon as an asteroid's discovered, you can know about it too, right?
That's
I mean,
right.
it's out there. Yeah.
So maybe you took the Planetary Defender quiz, it whet your appetite, and then you want to join us. We'd be happy to have you.
You bet.
Okay. So Nancy, talking about our little asteroid here, our little football stadium full of rocks. James Taylor on YouTube wants to know, do you know the composition of these two asteroids, especially the one targeted for impact?
Yeah, that's a great question. So what we do know from ground-based observations, again, is the larger one, Didymos, is a S-type asteroid. It's an ordinary chondrite-type meteorite material. This is actually the most common type of material that falls to the Earth. We haven't actually directly measured Dimorphos, but the way that we think that binary asteroids form, these double asteroids form, it's going to have a similar composition to the main one. So good likelihood that it's going to be made of this ordinary chondrite material, which ordinary chondrites are mixtures of rock and metal mixed together. They're 4.5 billion years old. They predate the planets. They're fascinating just from the science that you get from them as well. But it also makes it really relevant because it's the most common type of thing to hit the Earth. So that makes this a great test and a very appropriate test for DART.
Okay, so Jay has a very practical question on Facebook. For someone who's interested in entering a field like the three of yours, science or engineering, what basic courses do you suggest to set you up for a career involved with a NASA mission?
That's a great question. I'll give some of mine and then we can all jump in here. For me, I got started doing math and physics, and I think that's probably fundamental for a lot of things, but I would definitely encourage math and physics for sure.
Yeah, same. I love math and physics. That's something I really enjoyed in high school, so I decided to keep going with it. Engineering sounded cool. You're solving problems, building things, so that's what I went with.
Yeah, I have a PhD in planetary science. I was just fascinated by planets. I blame Star Wars, which I loved from an early age. But I guess also one thing I want to stress is that you should do what you're passionate about, and that it really does take all types to do this NASA missions. I mean, if you could look around where I am right now, you would see people with lots of different skills. And I mean, communicating is an important part of this as well,
yeah,
right?
If somebody had told me when I was 17 years old that science communication was a job, I would not have taken the sort of circuitous path that I did. I'm glad that I did, though, because lots of different skills go into this, and when I was in school, social media wasn't even a field.
Right. Well, Nancy makes a great point. It's something when I give public talks, especially to kids, try to always emphasize that, people say, I want to work for NASA, but I'm not good at math or science, or I don't want to be a scientist or an engineer. So, well, we have lawyers, we have financial people that do our budgets, we have communications people, we have artists, we have animators, we have policy people that help us deal and work with Congress. We have so many different skills that are really required, and we can't do a mission like DART or any of our missions without all of those skill sets. So you're absolutely right.
Yeah, I mean, and if you think about planetary defense, like everything we were talking about, right? I mean, this has a lot of implications beyond just, the science and the engineering to make it come together, and then what that is going forward. And I think that's one of the things I really love about working at APL and on missions and with NASA missions and this sort of thing. Just so many different people coming together with a common goal.
Okay, well, you are all smiles, and I've got the warm fuzzies about collaboration and the village coming together. This is going to be our final question. Kivo Bellone on YouTube wants to know, what's been everyone's favorite moment or part of the work that you have done on this mission?
I think my favorite moment's going to happen tonight so far.
I mean, agreed.
So I'm going to go with that. I'm just so looking forward to the launch tonight.
Yeah, so one of my favorite moments was, I was with this spacecraft from its youth until its adulthood, and part of integration and testing was testing it. So after this was a bare structure, we put it all together, and then we put it on a vibration table, and seeing that spacecraft shaking on a vibration table, it was crazy. I thought we were going to break it, but of course, analysis, we did not break it, and it survived, which means it will survive launch loads. So that was really cool to go through the whole testing process and just see the spacecraft grow up.
That's so cool.
There's been a lot of amazing moments so far, but I am going to say that my favorite moment is still to come, for sure. So I'm looking forward to DART getting off the planet and going over to Dimorphos.
All right, well, I know that you are all very busy, and everyone here, myself included, is all at Twitter about this launch tonight. So thank you so much, Lori, Lisa, Nancy, and to all of you, thank you for joining us. This show, NASA Science Live, is nothing without you. You are part of the conversation, and we're so, so happy to have you. So thank you. And know that you can learn more about DART by visiting nasa.gov/DART mission, and join the conversation on Twitter and Instagram by using #DART mission. Launch is literally hours away, and we do not want you to miss it. So you can set your reminders, set your alarms, and know we're streaming live on nasa.gov/live, NASA television, the NASA app, YouTube, Facebook, Twitch, Dailymotion, Twitter, wherever you get your socials, we're going to be there. And we want to hear from you. DART is set to lift off from Vandenberg Space Force Base at exactly 10:21 p.m. Pacific time, because it's an instantaneous launch window. So we launch tonight at that second, or we try again tomorrow or the next day. We hope that you'll be watching wherever you are. Thanks for making some space for us, and we will see you online.